Modern computing relies on a carefully maintained illusion. Underneath that interface is a dense labyrinth of metallic circuitry and raw data, intentionally hidden by the operating system to simplify the user experience. This design creates a critical problem for investigators. When a system is compromised or data is deleted, the standard interface becomes a filtered, unreliable view of the machine's actual state. The OS on the left reports a 0-byte folder, but the raw disk on the right reveals a dense grid of hexadecimal characters. The data is physically present. To conduct a legitimate investigation, you must bypass the OS and interact with the storage directly. WinHex functions as this direct interface. It provides unmediated access to the binary storage, allowing an investigator to see the disk exactly as the hardware sees it. We are going to deconstruct how WinHex reads physical sectors, interrogates active memory, and extracts evidence that the operating system would otherwise hide. Effective digital forensics requires shifting the perspective from the user's workspace to the physical state of the hardware. At its lowest physical level, digital storage has no inherent structure. It is a continuous stream of ones and zeros, representing individual electrical states. Reading raw binary is inefficient. We group bits into 8-bit bytes. Hexadecimal further simplifies this. Any 8-bit byte becomes 2 alphanumeric characters. WinHex compresses massive binary volumes using this system. It turns abstract electrical charges into a structured, navigable grid of hex pairs. While the hex grid provides precision, it lacks context to identify textual information. By placing an ASCII translation column next to the grid, WinHex reveals hidden plaintext strings that were previously buried in the raw data. Hexadecimal serves as the foundational language for seeing the structural reality of these digital artifacts. The logical file system acts as an invisible map used by the operating system to organize raw data. Standard file managers interact only with this map. They are essentially blind to any data existing outside the boundaries defined by the file system. When this map is corrupted, standard tools lose their direction, even if the data remains intact. The WinHex disk editor allows an investigator to bypass this map entirely, making direct contact with the physical sectors of the drive platter. This allows the software to parse partition structures and file allocation tables directly from the disk, supporting multiple file system types without relying on the OS's interpretation. The investigation also extends to volatile storage, random access memory. RAM contains active, unencrypted system processes, making it a priority for responders looking for live threats. WinHex can dump these memory contents and interrogate them just like a physical disk, allowing for the identification of malware artifacts or encryption keys currently in use. Bypassing the OS layer provides an unmediated view of storage, revealing data that malicious software may have attempted to logically obfuscate. When you delete a file, the operating system rarely erases the physical data. Instead, it deletes the logical pointer and relabels that space as unallocated. Because the raw hex data remains in this unallocated space, the file can be reconstructed using specific signatures. We look for magic numbers, unique hexadecimal sequences at the start of a file that identify its format, regardless of what the file extension says. WinHex allows analysts to scan a partition for these specific hex patterns, even if the file system no longer recognizes the file's existence. Once a header is found, the analyst can carve out the subsequent data blocks to reconstruct the original file. Recovery is only possible if the operating system has not yet overwritten those specific physical sectors with new data. Reconstructing files from unallocated space relies on the methodical identification of these orphaned structural patterns within the physical storage. Direct access to physical sectors is dangerous. Because WinHex can write directly to the disk, a single mistake can irreversibly destroy evidence. To prevent this, forensic work follows a rigid procedural workflow to maintain the integrity of the data. This process begins by defining the objective and securing evidence. The most important rule is an investigator must never analyze original evidence directly. Instead, a bit-for-bit forensic image is created. This working copy ensures the original evidence remains untouched during examination. Cryptographic hashing is then used to mathematically prove that the working copy is an identical match to the original source. Only after validation does the analyst move to identifying the file system and extracting the relevant hex patterns. The workflow concludes by documenting findings and preserving the investigation records to ensure the evidence remains admissible. Technical skill is only effective when supported by an unbreakable chain of custody and rigorous methodological documentation. Digital forensics depends on stripping away the software interface to observe the raw reality of binary data. But the evolution of digital hardware is creating new obstacles for these traditional techniques. Advanced SSDs with internal garbage collection, high-speed NVMe architectures, and cloud storage environments make it harder to isolate specific data at the physical level. As storage grows and AI-driven analysis becomes more common, identifying individual bytes manually becomes a more complex task. Even with automated tools, manual byte-level investigation is required to validate findings and analyze threats that automation might miss. As long as information is stored in binary, the ability to interpret raw hexadecimal data remains a prerequisite for validating the integrity of digital